Hello everyone, and welcome to the NEATEC Electronics series. This episode is about the field effect transistor, so let's get started. Alright everybody, so let's talk about the field effect transistor. That's what the F, the E, and the T mean, field effect transistor. Now we're going to talk about, there are many types of these, but this specific portion here, we're going to talk about the JFET, alright? So if you think about the JFET, let me just draw the basic structure. You're going to have a wire lead come in, alright? This one specifically is called the drain, alright? Now, think about it like this, alright? There's the body of the JFET, okay? Now, we're going to have part of the gate come here. Now, let's go back here. You're going to have another wire come in, and this is the gate, alright? And this part here that I drew, right, that's going to have a different dopant. For example, when I'm drawing here, let's call this an N channel or an N type, right? That means this gate is going to be P-type, okay? And we're going to have another wire coming out, and this is going to be your source. Now basically, how this thing works is you can control a channel here for the flow of electrons. So remember, that's just an example. This blue part, that's your depletion region. It's depleted of charge carriers, because remember, you have a PN junction here, right? So depending on the voltage on this gate, you can increase or decrease this depletion region. And how I drew it, you can see this. It's quite narrow here, so the amount of current that can go through there is restricted, right? Now, if I reduce the if I change the voltage, I don't want to say reduce because that's not a good way to say it actually. But if I change the voltage, I can change it so this depletion region basically gets very small, which case it's like this practically, it's like not even there, or I can make it very big, in which it completely closes the channel, alright? So this part here in the middle is called the channel. This is an N channel JFET, okay? And you control the channel by the voltage at the gate, alright? So that's a visual, and the symbol is over here on the right. So if we take this symbol and bring it up here, what we have here, this is the gate, this is the drain, and this is the source. Notice the arrow is pointing this way. For an N-channel resistor, the arrow points toward the transistor. A P-channel, it points away. Alright? Those are the two key things I wanted to get across immediately so you understand this. All right. Now, next I'm going to draw a circuit and try to show you how the current varies with voltage. See you soon. So now we have a circuit for you, and let's describe the circuit, okay? So this part right here, as you can see, just putting a dotted line around it right there. There is your JFET, all right? That's your transistor. The arrow's pointing towards it, so it's an N channel, right? So we have an N channel, JFET. Now, this is a resistor up here, obviously, right? So remember, with a JFET, you have your gate right there, your drain on top, and your source. The way I remember that, gate, drain, and source, the source is your source of electrons. They're going to come from ground. And drain, that's your drain of electrons. So that's where they leave. So remember, when you think about this, we always think of current going from positive down to ground, but actually electrons are flowing in the opposite way, all right? So anyway, that's how I remember this. And your gate, that's the voltage at the gate, right? That's what you're going to use to control it with. Here we have a battery, and we have this arrow. That means it's variable. So you have a variable power supply here. And this is minus on the top and plus on the bottom. So the greater that voltage, the more negative your gate becomes. All right? Because you've tied your positive portion of the battery to ground, right? You have your power supply for your drain source, right? So this is, you have the negative portion attached to ground. The positive portion obviously is not. So, and this doesn't have an arrow in it, so it's not variable. So it's set to a specific value, okay? So how this thing works, right, is suppose we have this voltage set here, okay? So this is your current I right over here. And this is your gate voltage V, right? Now, your current is going to have a specific value. Suppose the voltage is such that your channel is not closed and it's not fully open. It's somewhere in the middle. Now, if you increase this voltage, that's what I'm saying, it's getting increased. In other words, it becomes more negative, right? This voltage is increased, but it's more negative, all right? Well, what's going to happen? What's going to happen, okay, is your gate, your channel is going to change, right? It's going to either get wider or thinner. So in this case, the more negative, your channel is going to get thinner. And that means your current I is going to become less. Right? And the other way, if you turn the voltage this way, right, in other words, you were making it more positive, that's a plus sign there, more positive, then this current is going to become, you know what, I drew that on the wrong side, didn't I? Why don't I do that? It's going to become less. I'll just move that over there for you. Less is on this side. And then this is just going to become more because it's more positive. Got it? That means if it's more positive, that means, or you can say less negative. That might be another way to say it. your channel is going to get wider, which means it's going to allow more current to flow. So if you want to look at it, by changing this voltage at your gate, you're changing the amount of current that flows through here. These are very powerful when you think about that, all right? So that is basically what I tried to draw for you there. I hope that came through. Now there's a couple of things I want to show you about terminology. You need to know what VGS means. VGS, okay? So VGS, obviously the G stands for gate and the S stands for source, right? So that's going to equal VG minus VS. In this case, your voltage is going to be negative, right? Because you have a negative power supply here. So whatever that is, it's going to be minus VG, whatever it's set to, okay? Minus VG. Minus, now your source is connected to ground, isn't it? So it's going to be minus 0 volts. So VGS is going to be equal to minus VG, whatever that is at your gate, right? So depending on your circuit, your source may have a value, and you'll see that later. But I want to make sure we had that terminology straight, all right? Now, additionally, whenever you see a graph of these things, let's just draw a quick one right here. And this is going to be VDS. VDS is the voltage across your drain and source, okay? So for example, in your bipolar junction transistor, you had a base, a collector, and an emitter. It's similar to VCE, all right, except this is VDS. So it's the voltage across here, put a volt there. It's that voltage right there. If you have two leads and you touch each side of that transistor, it's your voltage, okay? ID, that's your drain current. That's the current that's coming down through your transistor to ground, all right? That's what ID means. Now, in the next part of this video, we're going to go over some charts because I want to show you some characteristics about the JFET. Okay, I'll see you soon. Alright, so one characteristic curve of the JFET I just wrote below. And you can see, here's your drain current, right? And here is your voltage across your drain and source. Now, this region right here, between this point and this point, that is termed your ohmic region. And you can tell because your voltage changes with your current. It makes sense, right? It's not, it doesn't flatten out. Now, it flattens out at this point, right? Between here and here, right? This is termed your active region. Now, beyond here, all this is termed your breakdown. Obviously, you don't want to be in that region, right? Look, actually, you want to be in your ohmic region. Let's be honest. This is where you want to have it running. So you will have a stable current for a variety of voltage levels from your drain to source voltage levels. Now, IDSS, this occurs when VGS equals 0. That stands for your drain current source shorted. Okay? So remember this kind of diagram, right? Once you get to this voltage, oh, by the way, this voltage right here, this is called, actually, this point right here, that's known as VP, which is equal to your, or stands for, your pinch off voltage. Alright? So this, the pinch off voltage is at the point at which your drain source voltage, where your current levels off and becomes constant. Now, VGS off and VP, right, are always equal in magnitude but opposite in sign. Now, we haven't talked that much about VGS off, and we're going to do this in a minute. But generally, I'm trying to draw this graph for you, and I'll draw it better in a minute. This is your VGS curve. Alright? Here it's going to be VGS off. Now, notice this is negative, right? This is for an N channel. But when you get so negative, at some point, the current through, this is 0, 2, and then this is 0 here. The current through the drain, right, the ID is 0. That means it's off. Obviously, you're not letting any current go through there. Now, as you change the voltage in this direction, it becomes less negative. You're allowing more and more current to flow, right? Until you have 0, VGS equals 0. When VGS equals 0, you are at IDSS, and that's the maximum current you can allow to flow through there, since your current is at its widest. Alright, I think that's what I wanted to tell you about this. But let me just finish. VGS and VP are always equal in magnitude but opposite in sign. A data sheet will give either VGS off or V pinch, but not both. Remember that. So if you're doing a lab and you have to look up the specific parameters in a data sheet, remember they're only going to give you one of those. Alright everyone, I'll see you shortly with some more information on the field effect transistor. See you soon. Alright, so what I did is I brought up the prior circuit here, and as you remember, this is a voltage source, a variable voltage source. Here's your transistor. This is your, usually you call this your VDD over here. I'll put that here, why not? I'll call it VDD, right? So here's your positive source. This is going to drive the current. It's going to go through your transistor. And remember, these were prior drawings I put here, so these are not connected. That was just showing your current, okay? So, just kind of cleaning this up for you here a little bit. Now, I drew here below, you can see I drew VDS, not VGS, VDS, and I drew ID, right? Drew it, I created a chart with them, alright? So here's your ID, and here's your VDS. And at VGS equals 0, this is what your curve looks like, right? Now I only drew it up to break down. I didn't continue this number. I'm just looking at the active region, okay? Now what's going to happen if we increase this voltage, for example, right? So now your voltage is going to be -1 volt. Well, let's just think about it. -1 volt, the more negative volts you get, that means the thinner or the more narrow the channel is, which means there's less current that's going to flow there, right? So if you're past the pinch-off voltage, the maximum current you're going to get, now this is just an example, let's just say that it's down here. Alright, so it's going to come here and then it's going to come down right. I tried to draw that pretty well, that's not too bad, huh? And this is going to be VGS equals, let's just call that -1 volt, alright? Now what happens if you keep on increasing it? Well, suppose you want to go to -2 volts. Well, that's going to further close the channel, or narrow the channel. I'm sorry, I shouldn't use the word close. It's going to further narrow the channel. And as you do that, the maximum amount of current you're going to be able to get is going to decrease. Get it? VGS equals, say, -2 volts, for example. Now, at some point, you're going to increase the voltage, so you're at, you recall, let me draw this here for you. You remember you have this chart here, and this is IDSS, and this is VGS off. This is VGS, this is 0, and this is 0, right? So at VGS off, remember this is VDS, this is VGS. They're different, right? This right here is specific for your transistor. Now, at VGS off, how much current do you have going through there? You have 0, don't you? So you increase the magnitude, which means you're actually headed this way, right? You're increasing the magnitude. The polarity is negative, but you're increasing it and increasing it until you hit that VGS point. Then your current is going to be right here. It's just going to be 0. So depending on the voltage you have, you can have all these lines. You're probably going to see this in literature. That's what they're talking about. So depending on your VGS voltage will give them the current, the constant current that will come out of your transistor, that your transistor is able to allow to pass. Alright? Until you get to VGS off, and at VGS off, alright, that's what this is. This last one I drew here is VGS equals VGS off. Alright? That means no currents flowing. Now, alright, I'm going to go into this next. I want to talk to you about this to make sure you understand more about that specific chart. Okay, everyone, see you soon. Alright, everybody, so you probably recognize this chart, or graph, I'm sorry, it's a graph, but what you have here is VGS right here, right? And you have ID here. This is really ID, and this is the point right here, IDSS, when VGS equals 0. Here's VGS off, and actually, yeah, you can think of that as minus VGS. That's what it is. And over here, if it went over this way, this would be plus VGS, right? But since we're talking about an N channel, it doesn't go there. So there's a relationship with this chart that you really should know, all right? So with IDSS, if you divide IDSS in half, if this is IDSS over 2, okay? Whatever this current is, if you take half of it, you come over here, right? And then you come down. This point right here, this is equal to VGS off, okay, times 0.3 volts. Okay, it's a 3 there. If you come down, if you divide that in half, and you're basically at IDSS over 4, okay? And now you bring this here, and you come right down. This point right here, that's equal to VGS off times 0.5. All right? So this relationship is very useful when you're doing problems. That should be parentheses there. This relationship is very useful when you're doing problems, right? So, yeah, generally this is a target area right here. You want your circuit so that generally it's going to operate around this region, around half. This way you have a lot of room, right? Between 0, you're not, if you have if VGS can vary, if you're looking at a voltage, it can vary quite a bit. As long as it varies so that your ID doesn't attempt to go beyond IDSS, or your VGS obviously won't go lower than VGS off, it will always be on this curve, all right? Now, one other thing that has to be said about these transistors, and I want to make sure you understand it. Generally, this is with all field effect transistors. The field effect transistor relies on a field, right? So, in this case, I'm just making a diagram here of your JFET. Why don't you draw it along with me? And this is going to be your gate. That's going to be your drain. That's going to be your source. And then your gate material, your p-doped material, is going to come in here, right? Now you're going to have to reverse bias this, because remember, this is P. This part here is N-type material, right? And when you reverse bias, that means you're going to apply a negative voltage to the p-doped region relative to the n-doped region, right? And that is going to create your depletion region here. And if you recall from the diode, in the p-n junction, the greater that voltage, the greater the depletion region, right? Because it widens. And when it widens too much, it's going to make this narrower and narrower, and then when it gets large enough, when each one of these depletion regions gets large enough, it's going to close off the channel, so there's not going to be any current flow. But I wanted to tell you that the current I in the gate here is very, very small, right? very small. I think I drew that well. That's one of the benefits of the field effect transistors. All right, they're voltage controlled, and the impedance on the gate is extremely high, which means the current is very low. So you're not going to load down your load down your circuit. I'm sorry. So remember, when I say load down your circuit, what I'm saying is you're not going to sink a lot of current out of your circuit. So high load, that means high current, right? And low load, that's going to equal low current, right? So, sorry, I didn't spell that right. I want to make sure you understand this. Generally in circuits, you've already, I'm sure you've already built circuits by now. You understand that you calculate the current and the resistance and the voltage and all this works together. And if you want to add a switch at some point in your circuit, if you add a switch which takes quite a bit of current, in other words, is relatively high load on the circuit, that's going to change things in your circuit, right, which you may not want to do. So that is one of the big benefits of these field effect transistors, okay? So remember this relationship. This is important. And let's do something real quick right now while I got you here. I'm going to move these. Delete. Now, let's draw something here. And you may see this in literature, you may not. From this point over, this is VDS, right? So if you think about it, if this is ID, what did we say that looked like? If you recall, it came up here like this. I'm just going to draw it up as best I can. And then we went to the pinch off voltage, and then it did that number, right? And this, between this voltage and this voltage, right? This was your active region, wasn't it? ACTIVE region. Now, suppose the current had changed and now it's at this level. I'm sorry. Suppose your voltage, your VGS changed, and now your current changed as a result, and it is right here. It's this is IDSS, right? IDSS. So let's say this one is IDSS over 2, right? Well, what do you think that curve's going to look like for VDS? It's going to go up, up, and it's going to get somewhere like this, and then going to go off, right? What happens if VGS changes and now you're going to be at IDSS over 4? I'm sorry, wait a minute. Draw that right here. Over 4. Well, I'm sorry, that's IDSS over 4. It's getting kind of small there. Well, what's going to happen? We're going to come over here, aren't we? Then it's going to level off here, isn't it? So if you notice, as you change your VGS, you change the amount of current that can go through your transistor, and that current then results in a change in your curve here with VDS. You notice that your current obviously is less. and then at the point you get to VGS off, you're at 0 again. Okay. All right, everybody. That's the. Those are the charts I really wanted to get across to you to make sure you understood how the JFET actually worked. And these charts you're probably going to see in the literature often. All right. Remember, what's this voltage right here? I can't leave this. I can't leave this too quick. Where is it? There it is. What's that voltage right there? Remember, VP. What does that stand for? Pinch off voltage. I'm not exactly sure where they came up with that name either. All right, but anyway, that's what it is. All right. All right, everyone. See you soon. All right, everyone. So finally, in this field effect transistor video, I would like to go over one more type of field effect transistor, and that is the MOSFET. Okay, metal oxide semiconductor field effect transistor. That's a mouthful, isn't it? But anyway, this is the diagram of what you're going to see on a schematic of what it looks like, and it's this item. I'm going to draw a circle. That's what it looks like. Okay. Now, how this particular item is engineered is you need a gate of voltage, obviously a voltage put on the gate, right? And what that's going to do is create a bridge. The JFET, we talked about a channel. The MOSFET, we talk about a bridge. Okay. Now, there's two types of MOSFET. There's an E-MOSFET. That stands for enhancement. And we have a D-MOSFET. That stands for depletion. Now, you can see this MOSFET, it has a gate, a drain, and a source, just like the JFET. Here's your arrow. It's pointing in towards the transistor, right? Here's your little arrow right there. It's pointing in. This is your N channel. This one, the arrow right here, that's pointing away. So this is going to be your P channel. Okay? Now, I'm going to get out my eraser and erase those things here real quick. Just make sure you guys get that. I don't want to mess this up on you. There we go. Now, notice this fact right here. I'm going to put this in blue so you see it, because this is how you can identify it. Notice that for the E-MOSFET, okay, this line here on your transistor here, then there's a space, there's a break, and then it comes over here, right? And the same thing obviously is on your P channel, right? There's a break there. It's not continuous. That's a way to identify your E channel, your E MOSFETs. I'm sorry, not E channel. Forget I said that. It's an E MOSFET. So what that means, if you look at the chart here, this is VGS, okay? That's what, if you recall, before it was rather different because for the JFET we went off in this direction, right? And it came up like this. Well, now we're talking about a MOSFET, so it's different. So VG is here, VGS, I'm sorry. And this is ID. okay? Here you're going to have a voltage called VGS, and this is your threshold voltage, okay? Now, what's going to happen when you reach that voltage, your current's going to start flowing, right? So as soon as you reach the threshold voltage here, right here, it's going to then create enough of a bridge to start allow current to flow. The greater the voltage, the more current, the bigger the bridge, the more current can flow. All right. So that is your MOSFET, and that's how you identify it. And this is the chart for that one, right? I'm not going to go into the P channel, but basically, well, why don't I just do this for the heck of it, right? Your P channel is going to be, here's your VGS, right? And what's going to happen, here's your VGS threshold. By the way, it's negative, obviously, right? This is your ID. And then if we look at the chart, it's going to do this same thing, like that. But that's the P channel. I really have not concentrated much on the P channel in our discussion. I've always used the N channel. All right, so there's your MOSFET, specifically your MOSFET. Now, give me a second. I'll be right back, and we're going to continue this discussion with the D MOSFET. See you in a minute. Well, I'm back, and as you can see, I have gotten rid of the two charts below here, okay? I have not changed the actual schematic diagrams of the MOSFET because I want to show you it's they're very similar, the D and the E, as far as how they're drawn, but here's the change. So watch this one right here. Watch this one. To make the diagram a D MOSFET, I simply get rid of that. How they do it in the book, they do a check here, right? Same thing here. Same thing on the P. Alright? The key thing to remember here is that there is no break. Okay? So what does that mean? Okay? I'm sure that's a burning question that you want to have answered. So if you look at it, here we are. Let's draw this again. And let's say this right here is IDSS, okay? And let's say here is VGS. We're going to call this VGS off, okay? And by the way, this obviously is VGS. It's negative here. So what we need to do then is to draw our curve, right? It's going to come up something like this, and it's going to cross, isn't it? That means your VGS is going to be here, isn't it? It's going to actually kind of be positive. So this right here is 0 volts, right? So basically what this is saying is if you have a circuit and there's no voltage at the gate, suppose your gate voltage is just say 0, okay? If you make that voltage negative, that means you're going to get less current, right? Because your current's going to come down here, isn't it? The more negative you go this way, the less current. If you make this current, if you go negative, negative, that means less current. current, right? If we go positive, that means more current, because now you're on this side, aren't you? And you're going to get more current. So your DMOSFET obviously has a different curve. There's obviously no threshold voltage for your DMOSFET because it can operate and it will allow current to flow at 0 volts. Okay? But if you recall, your eMOSFET will not because there's no bridge. So when you look at this, it's kind of intuitive. When you have a bridge like this, it's already there. It's either you enhance it, think about a car bridge, you enhance it, you make it wider so more cars can go across, in other words, more electrons can flow, more current can flow, or you deplete it. In other words, you take away lanes so fewer cars can go across the bridge or fewer electrons can cross the bridge, and you get less current. All right? So again, these are field effect transistors. So your current here at the gate, I, is very small. That's why these are used so much, is because when you create the field there, it doesn't load your circuit. If it doesn't load your circuit, that's a good thing, right? Because that means you don't have to go into extensive designs to take into account a big load, should you have to do that. Now let's just talk about this side, the P channel, all right? The P channel is going to look like, it's like a bookmark kind of this kind, right? If you look at it like this, look at it like this, you have VGS off, you have IDSS, and we're going to connect these two. I'll do this the best I can now. It crosses 0. Remember, this is your 0 volts. VGS is 0. So again, it has the same behavior, but this time if you have less VGS voltage, in other words, it's more negative, you're going to get more current because it's on this side, right? So if you come over here, your current's going to go up. And if you're on this side of it here, your current's going to come down, right? And that's about it. Now, with these MOSFETs, there are equations that go along with them, depending on the text you use. You're going to have different equations that go along with them. So I'm not going to go into that here. I wanted to give you a basic idea of a MOSFET and how it works and why they're so useful. And I just don't want you to underestimate this right here. Your gate is very small, and you can turn on or turn off your MOSFET quite easily to allow your current to flow. And that would, obviously that would be an eMOSFET. Or you can if you have a 0 voltage, you can give it a little more voltage to get more current, or a little less voltage to give less current for an N-channel device. And this is, by the way, I didn't even mark that down, did I? This is your N-channel. And this is your P-channel. I'm sorry, I should have written this earlier. Alright everyone, I hope you found this video useful and has helped your understanding of the field effect transistor. Thank you very much.